Okay, good afternoon. I'm in a kind of a new role here because Josef Urban, who was the head of the department until late last year, left CIRC. Also, Tomáš Mikolov left CIRC. So a lot of things have changed. So now we have 4 groups in the department. One led by Babuška on machine learning, and one led by Jan Hůla that is trying to explain machine learning, so it's mainly about foundational AI. I myself am the head of the formal methods group, and Martin Suda is the artificial reasoning group. We have around 22 kind of fixed positions in the group, a number of students. We mainly publish at conferences, but there are also some journal papers. So I counted 8 journal papers and 7 core A-star. So A-stars, who doesn't know, A-stars are typically more difficult to get accepted than journals. We participate in a bunch of projects, and we organize events. So I don't have much more to say. And we can move to Martin, or no, wait.
Funguje to? Okay, hello. So I will talk about our recent effort about where we try to automate parts of machine learning research. We are mostly doing it for making research more fun for us. It's very much work in progress. So we are just starting, but we are very excited about this direction. So I thought that I would rather talk about this than about something which we did in the past. And I hope it could be useful for some of you. Typically we are doing research in machine learning, and it has its own specifics. So first, it's extremely empirical. It's very hard to predict whether something will work. Ideas need to be tried. And also we are very lucky that most of the experiments are computational. We don't, everything runs in a computer, and there is not much danger that we would damage something. In the worst case, we just waste computational time. And how does ideal paper in this field look like? Or maybe one type of ideal paper. It has a very compactly describable idea, which has big impact on performance. So there is an example of residual layers, which is extremely well describable, and it has nice impact on performance of neural networks. And why we like this kind of papers? We like them because they allow us to easily combine or modify ideas. We can take many such ideas and combine them together and try new combinations. And most of the research in machine learning actually is about this, about combining ideas, about modifying them. And if you look at it, it looks a bit like an evolutionary process, which is a bit blind. People are sometimes trying random combinations, and somebody is sometimes lucky. He discovers something, other people copy the idea, they modify it, combine it further, and in this way the process, the research goes on. And with the advent of capable language models, many people realize that it should be possible to somehow automate this process. These combinations and modifications, because we have always been doing some kind of local search where we would have some idea, and we would explore the space around this idea by doing hyperparameter optimization, where we try different hyperparameters and we see what works or not. And with LLMs, we probably can do something broader. We can probably explore in the space of ideas and space of implementations. So that's something very exciting, but we are currently working on something more basic, which is replication of machine learning papers. So this could be very nice basis for the later evolution, because the replicated papers could be, the things which can be combined and modified. But it's also practically useful by itself, because we often need to do baselines for papers, and it's sometimes very annoying when during review process somebody asks you, please compare your method to some other baselines. And it may be not trivial to like do it, so sometimes it's quite annoying. And it's also very good to have a code instead of the paper, because in the code you can sometimes like better understand what's going on. You can see what happens during execution. So having this process automated will be very, very useful. So that's what we are trying to do. And we are currently experimenting with this on a topic where we have some expertise. It's graph neural networks for Boolean satisfiability. And what we did, we downloaded relevant papers about this topic using ASTA API, which is serviced by creators of Semantic Scholar. And then we filter papers using LLMs, where we have some criteria, which, like, for example, we want only papers which are about supervised learning. We don't want papers which take too much to train them. And we collect around 20 papers, and now we are trying to replicate them with minimal effort. So first, we want to understand what's in this paper. So we are experimenting with a dynamically built UI, where we have some query, like, for example, what kind of contributions are in these papers. And then the LLMs go over these papers, extract the information, and then they synthesize a code which will visualize this information in some easy to understand manner. So here is an example. We have this UI where we can click on a paper and see what kind of papers, experiments are there. So thus far we replicated 4 papers where the manual effort was under 1 hour if we don't count the training time. And we realized that it's much more beneficial if we do it more like a methodology where we provide some high-level decisions instead of doing it like an end-to-end system. One paper looks like we implement separately the benchmark and the method. And because in the paper usually there are many experiments, and we don't want to replicate them all. We just need the baseline, and we need to have some kind of certainty that we did it correctly. So the minimal thing which we need to do is just to take the baseline and apply it on some benchmark on the paper and see that we have approximately same results. So for example, we'll tell the LLM we need the experiments in table 1, first line, second column. And this would correspond to some concrete benchmark and some concrete method. And we do it separately from benchmarks, separately for the method. And we do it in 2 phases. We first ask the LLM to extract specification. So the LLM will read the paper, extract the specification for the coding agent, and then the second phase, coding agent takes the specification and tries to make it work. So we run the coding agent in a debugging loop where we basically ask it to implement the code and make sure that it trains. And it can implement the code, try to train it, it will see there is an error, it will fix it, and it will continue until it works. And then we manually train it and see whether we have same accuracy or performance as in the paper. And if not, we need to fix it. And we asked the LLM to suggest possible inconsistencies. We manually check them. And if there is something suspicious, we ask it to re-implement. And so that's this. So we are still experimenting about how to do it properly. We are doing ad hoc stuff, so we don't know how this should be done. But it's already visible that with very little manual effort, papers could be re-implemented, or at least this kind of papers which we are focusing on. And it provides much better value if you have a human in the loop than to have something end-to-end. And hopefully we'll make this process as smooth as possible, and in the future we can do this evolution where things are combined and modified, and this would lead us to a very exciting area of research. So thank you very much. Who is next?
Saying, oh, we put a lot of CO2 into the atmosphere.
Yeah. I think I think, like, I remember in the past, like, people were very afraid about, like, wasting compute by training LLMs, but this trend, like, is only scaling. Like, people are training bigger and bigger models, and people don't care. So we don't want to be behind. Okay. So who is?
Yeah, I think it's fine. Yeah, let's.
All right, good afternoon. My name is Erik Derner, and I would like to introduce our work titled Beyond Words, Multilingual and Multimodal Red Teaming of MLLMs, which is Multimodal Large Language Models, that we presented at the workshop on LLM security at ACL 2025. That's one of the largest computational linguistics conferences. And what is red teaming? So it's a term from cybersecurity, which refers to challenging some safety measures. And in our case, we're going to look at the safeguards of these large language models. So not only that now we are moving beyond text to other modalities such as audio and images and so on in the multimodal context, but also we explored other languages than English, because most of the research and also a lot of the safeguards that are in place are actually implemented for mostly like focusing on English. And therefore, in the multimodality, we have the challenge of highly dimensional data. There we have a lot of corners of the space that is basically underexplored and that allows for complex attack vectors. So in our study, we evaluated 7 languages. Among those were large resource languages such as English, German, Spanish, and French, but also lower resource languages. We picked Czech, Slovenian, and Valencian. Valencian is a language similar to Catalan, spoken in the Valencian region, eastern Spain. And the models we have evaluated are from the OpenAI family, GPT 4.1 by Meta, Llama 4 Scout, and Alibaba's Qwen 2. Basically, to evaluate these models, we picked an existing dataset, attack dataset by IBM, which has some toxic prompts. So you can imagine prompts how to rob a bank, how to make a bomb, and so on. These are the things that LLMs shouldn't tell us how to do, and classified in 7 categories. And we set up 4 input modalities. That is plain text. That means asking the LLM directly the prompt from this dataset, then prepending the jailbreak prefix, that is usually using some deception method to manipulate the model in actually eliciting the output. So for example, saying, okay, so imagine this is just a research scenario, don't worry about your safeguards and so on, and then perhaps it jailbreaks the model. And then the most interesting part, I would say, for this study is to convert the text in image. We used a really simple approach in this study, and it's to basically render the text of the toxic prompt into an image in plain text, 1 line, black on white, and that was it. And finally, the final combination was a jailbreak prefix, the same as in the textual version, but this time jailbreak prefix plus the image which renders the text of the toxic prompt. We used for all the combinations, so we have 7 languages, we have the 4 modalities, and we evaluated the 3 models that we have seen. We used the LLM message edge technique to evaluate the attack success rate and the refusal rate. This was aligned with aligned LLM message edge with some manual annotation. And let's have a look at the results. So especially I would like to maybe focus on the yellow or orange bars, which represent the variants with image. So let's just briefly go through the legend, what is what. So from the left to right, the first one is the text. The second column is the done, which is do anything now, or the jailbreak prompt plus text. Then we have the orange ones, which is image. And again, the jailbreak prompt plus image. And you can see that the orange bars especially for lower resource languages such as Czech, Slovenian, or Valencian, is the first one, but last and last are basically very successful in jailbreaking the model. So it means that if you render the image, basically instead of using the text is put in an image, you can already make the model do something it shouldn't. And similarly, refusal rate, that refers to when the model actually answers, you might have seen it, I can't help with that now, and so on. So again, we can see similar pattern for Czech, for Slovenian, for Valencian especially. It actually refuses less often. So it's basically easier if we render the text of the toxic prompt as an image to jailbreak the model. Lower resource languages, as we have seen, are more likely to jailbreak the model. Then another observation is using the do anything now prefix actually increases the attack success rate more likely for text than for images. And yeah, we have run these experiments repeatedly, and we have seen that the results are consistent. So the main takeaway would be if we combine multilingual and visually rendered prompts, this actually jailbreaks the models. And how to mitigate this? We are doing this study to inform what are the vulnerabilities in the models and to inform how we can actually mitigate it, how we could protect the models from this type of attacks. So one option would be definitely to use OCR pre-filters to filter it at the input. So basically to see what text is there and see if that is something that shouldn't be responded, should be safeguarded. Then focus in fine-tuning on the multimodal alignment. Of course, also focus on other languages than English, because there are many users that are using other languages. And finally, some automated content moderation. That's it from my side. Thank you so much.
Mirek. Asi jsem tě nějak
wait. How does it work? Okay, fine. Okay. So I would like to tell you something about AI for IMO, which is which was getting quite some traction in the last years. So first I should just say what is IMO. This is this like funny, colorful picture which combines the math Olympiad, which combines the Olympiad colors with some kind of mathy stuff. But in fact, it's the most prestigious math contest in the world. It is a contest of high school students. There are almost all the countries in the world participating. They're sending, each country typically sends their best 6 students that get through some selection process. As far as I know, it's the oldest science Olympiad, whereas like now we can see others like economics Olympiad or I don't know, whatever, right? Like chemistry Olympiad, but IMO is kind of the thing that started this all. And there is a question like, this is of course a measure of intelligence that you can get to IMO, that you can get some good results. So we were like thinking about it as a challenge for AI, and already in 2018, I proposed it on this AITP, which is a conference organized by like Josef Urban, who was at that point at Schirk. And later there was someone like said, "Oh yeah, this is a grand challenge. We still have no idea how to do it. People thought how this is very hard, pretty much impossible." And that stayed for like 4 years, that people were thinking it's very hard. Although in the last 2 years, suddenly companies were making quite some progress. So in 2024, which is basically a year ago, and because the competition takes time in summer, DeepMind got silver medal, and next year both DeepMind and OpenAI got gold medals. But still, that doesn't mean that it's superhuman, still the best humans are better than the best AIs. So that's kind of the current status. There are 3 approaches that we can use for when we want to tackle this challenge. And that's kind of the question how we want to represent our problems. So one approach, which was, I would say, the first one, and it's still popular, is that you need to take a general language so that you can write arbitrary IMO problem in it. So nowadays, typically, this formal language is Lean, although like sometimes people use other languages like Isabelle or Coq, nowadays Rock. The other approach is that you don't care about formalism. You do not have any formal check how you tell if the solution is correct or not, which means that you just run some language model, let it think for a lot of tokens somewhere in private, and then you let it extract the solution somehow, and then you have to take the solution, bring it to a human checker, and ask him, hey, is this worth any point on IMO? How would you grade it as a human competitor? So that's what like OpenAI mostly did. And here I would like to talk a bit about more domain-specific and symbolic approaches, exactly. So just to show you 2 examples of a problem, there are like two problems from different years, from different categories, but they're good representatives what I want to talk about. One is a functional equation. So this functional equation is from the year 1992. And basically the idea is that you want to find all the real functions, that is functions from real numbers to real numbers, such that no matter what xy you plug into the equation, this equation will hold. So this typically is some linear function, maybe a quadratic function, maybe something completely like random and noisy. The competitor must figure out. And the other problem, the other kind of specific domain that we were looking into is geometry. So this is the last year's geometry problem, which I don't think I can easily, do I have, well, like, yeah, I will not try to explain exactly how it's built, but basically the idea is that the problem tells you that you draw some circles, take some intersections, draw some lines, and eventually you want to prove that the small circle which is in the middle is tangent to that line, which you kind of see from the picture, but you have to mathematically prove it. It's not enough to just see it from the picture, you have to prove it. What were we doing with this? We were looking into geometry for some time. So here I will just talk briefly about alpha geometry, but it kind of inspired the work that we were doing with geologic or other constructions, and functional equations, which is like purely our work. So the idea of alpha geometry is that they take the picture which is constructed by the problem, and then the first kind of the creative step is to figure out what to do, what new points to construct. So for example, here we construct this new point in the middle of the site. And the reason why we construct it, because after we add some additional constructions, this new point can help the symbolic deduction solver actually prove what it must prove. So after this construction is done, then it's just thrown into a symbolic deduction system, and this symbolic deduction system see, okay, now I can see there are 2 similar triangles, and because the triangles are similar, the 2 angles are equal. And that's how the problem is eventually formally proved. And with this approach, kind of DeepMind, but I was in their team, solved 37 out of 39 IMO geometry problems. And here we tried something very similar with functional equations, or like very similar kind of. It's functional equations are a bit harder. They're not as specific. Like the deduction is not as simple as with geometry, but we kind of scraped a lot of functional equations, not only from IMO, but from also other high school Olympiads from the kind of preliminary rounds to get to IMO. We got 343 sorry, this is not geo problems. This is typo. This is functional equations problems. And then what we did, we basically modified the heuristics for CVC5 prover to do some bits to like. I have to admit, Mikoláš would know a bit more about exactly what was done here. But the hard part is to figure out what to plug into the equation. So we need to solve this equation: fx plus y equals fx, etc. And the first thing you can do, okay, let's plug y equals 0, and that simplifies to fx equals x times f0. So if we know what f0 is, then we can solve it. And fortunately, we can know what f0
si rád
is.
trošku
We can just say, hey,
zaprogramoval.
if we plug x equals 0, then
Dobrý, tohle to
f0 is 0, and that concludes that f must be 0 globally. So that's, I believe, yeah, that's all what I wanted to tell you.
Co z toho programu to je?
CVC5.
Looks promising. Thank you. Okay, good afternoon, everybody. So my talk is titled "Vampire with a Neural Flair," and I will jump in and try to explain what it means step by step. So, as mentioned, we are doing automated reasoning, most notably automatic theorem proving, which is one of the classical disciplines of symbolic artificial intelligence. So, dealing with logic and not necessarily with real numbers per se, as machine learning does. But we will get to the merger soon. So first order logic is the language that we use to describe the world. So that's the hypothesis that you have to make, and we employ algorithms of logical deduction, which means deriving what necessarily follows from what's already established or stated. And what we cherish, what's kind of the staple, or what we really are after is a proof, right? It's even in the title of the discipline, some kind of witness that convinces everybody that what we are claiming is true, and it's not just conjured up. And this can be used for new discoveries in mathematics. We have application in hardware and software verification, where verification should be stressed. This is meant as like a much stronger version of testing, which testing can discover bugs, but verification can say with certainty that there are no bugs. So this is like a much harder but much more valuable result if you get it. And nowadays, for instance, Mirek mentioned Lean, which is a proof assistant. So, well, it can also be called a programming language, but in this context, proof assistant means that some person is trying to formally derive certain result, and the result is so hard that it wouldn't be easily achieved fully automatically, but that person is going to be happy if they are assisted by automation support, at least in some individual steps, and this is what automatic theorem provers are good at, often helping to bridge these boring deductions that mathematician would say, this is obvious. This is left to the reader, right? But it's still hard work if you want to convince the computer that this is actually true. Okay, so now what is Vampire? Vampire is an example of an automatic theorem prover that we are working on. It's a state-of-the-art system. We like to contest in competitions. One of the most famous competition in this field is called CACORR, so Theorem Proving Championship, and Vampire is a regular winner. Last year we managed to actually win all the 8 divisions of the competition, so 8 out of 8, which never happened before. But this is not just us in our group, but also some collaborators in University of Manchester, in TU Wien, and now at Southampton. Now the neural Flair. Neural Flair. So we have already heard about reinforcement learning, which is a machine learning paradigm where you have some kind of, you imagine your problem, you need to cast your problem into a situation where there is an agent that navigates a certain environment by choosing actions and getting rewards for these actions. And then this reinforcement learning as a technology can hopefully, if conditions are right, as a target, give you an optimal strategy, which is often called a policy, which will navigate the agent such that they can get the best possible reward. And neural means hints to the point that we are using deep neural networks as kind of the brain of this agent in this context. And you probably have heard about these successes coming from DeepMind already quite some time ago, more than 10 years ago, at least the first one, where they were teaching this agent to play computer games, just staring at the pixels and saying, now you should move up and so on. So it had to figure out the whole concept of how the game should be played just from self-play, which is quite impressive. And now the idea is to apply these techniques to improve a theorem prover. So Vampire is a saturation-based theorem prover, which I will obviously not into many details on explaining what it does, but just to point to the place which I'm trying to improve. So we have this logical calculus, that's the thing in the cloud, which are some formal rules of deduction about how we can derive new stuff from already established things, with the aim of finishing the proof through a sequence of such applications, of such steps. And then saturation is just a way of organizing this, in principle, infinite sequence of, like, you already have something that you've established, initially the axioms and the conjecture, and then you keep adding stuff. And saturation is just how do you organize the bookkeeping about what should be done next and what's already been done, and then there is some simplifications happening around to make it efficient. And you start from an input that's logical formulas of some general form, then you preprocess them, you get something that we call clauses, that are some kind of basic building blocks of logical formulas. And then at each iteration of this iterative algorithm, you pick a certain clause, you say, what if this one was part of the proof? What would happen? And then this kind of hints into the situation where this is very important place, right? If you kind of know already what you want to achieve, you would pick the right clauses and be done. But you don't know this up front, and because this is a semi-decidable problem, you will never know algorithmically up front. So, but if you focus on this heuristic, you can do a lot. Okay, we have basically discussed that. This is the basic reinforcement learning concept. Now, how to apply these concepts to what we are doing in saturation-based theorem proving. We will say the agent is the clause selection heuristic, the thing that we target for optimization. Then there is this ever-changing set of passive clauses that we are looking at and trying to pick the next most interesting one. So this is the action space for the agent. And then there is a lot of other things that you need to decide on when you are applying reinforcement learning. And you could aim for the most general thing, but then it's not going to run because it's going to be too expensive, or you will never collect enough data, and it would take forever to train. So these are the challenges that you need to figure out right. What also you need to do right, and it's challenging, is to design an architecture which turns the symbolic, the logical formulas, and the state into a form that neural networks can process. And for this, we need to use certain established techniques like graph neural networks and recursive neural networks. But again, the trick is to kind of care about expressivity and at the same time efficiency, because otherwise it would be either too slow or it wouldn't know enough about what's going on to make good decisions. And this is a picture that shows that it worked. Of course, there is a lot of things that would need to be explained in detail, such that you could put it into perspective and appreciate it for yourself fully. But we see some kind of cumulative graph where on the x-axis the time is increasing. It's a logarithmic scale, but it doesn't matter. And on the y-axis you see how many problems of certain set of test problems the prover is able to solve until that moment in time, if you give that amount of time on each of the problem. And the kind of the horizontal lines or the parallel lines at the bottom are some old techniques, and you can vary those techniques, and some are a little bit better. And for instance, like the step from one of the horizontal lines to the other one would be worth a paper already at a conference on automated deduction. But then there is this jump to the neurally guided prover that is dwarfing the other things. What you also see at the very left is that the neural network needs some time to even just start. So the good old-fashioned AI is still better if you only have a fraction of a second. But if you are willing to wait half a second to load the model and then start crunching the data, then it will soon become more efficient. Right, to conclude, it's time scale but measured in processor instructions, because this is more stable metric. But think time, and it's logarithmic, so yeah. Oh, roughly this is from 0. Yeah, it's from a second to minute, roughly. Yeah. Thank you. Yeah, so we had had some nice success with this neural architecture that is kind of conceptually built on reinforcement learning, and right now our servers are working on getting some more results and about like applying these techniques to the what's relevant for the users that I was mentioning, libraries of formal mathematics, where we could hope to speed up the workflow of users of interactive theorem provers quite a bit, for instance. So that's it. Thank you for your attention.